So good morning. So today we are going to see about how we can design a circuit and simulate with the help of a open source tool which is called as a digital schematic and a microwind. Okay. So let me open a software tool page. So since this tool is an open source tool, it does not belongs to any installation or it does not need any supporting files. It's just an open access tool. So as the first case, now we have to design a circuit. So for designing a circuit, let me use the tool called as a digital schematic. In short, it will note it as a dsch. So it is a digital schematic. So now I am opening a software tool. So here you can find many applications related circuits. Here, let me find with the name of the D. You can find with this icon as a dsch. The 2 is nothing but an version of the software. So it does not any bother about it. So now you can select the dsch2 and press enter or a double click. So for opening a tool. So after double clicking the dsch2, you can find this page. It contains a decimal lines. With the in the right side corner, you can find a library. So the library is nothing but an you can find the some list of components. So let me name it as a PMOS, NMOS, NOR gate, and then OR gate like this. Here you can find a components. Okay. So here you can find a file. It is nothing but done for opening a new file or to save, and the select foundry. Select foundry is nothing but done for the base material of the whether we can design go ahead with the 35 nanometer or 42 or 180 micrometer like that. So for an experiments, let me first design a basic CMOS inverter. So we are all come across with the VLSI topics. I hope you are know what are the components involving in the basic design of CMOS inverter. So let me read again and recall to you. So yes, basic CMOS inverter will have an one PMOS. So in this symbol library, you can find at the bottom P channel MOS. The P channel MOS is nothing but an our PMOS transistor. Okay. So just you can drag and drop the PMOS. Okay. So you can place it over here. So the next to the PMOS transistor, we have to drag and drop the NMOS transistor. So the nearer the component is N channel MOS, the N channel MOS is nothing but our NMOS transistor. So you can just drag and drop the N channel MOS, that is an NMOS transistor. So now we have placed over the PMOS transistor and then NMOS transistor. So here you can find the length and width of the transistor. Okay. So since it is an open source tool, we cannot change the length and the width. That is the size of the transistor. We are all come across with the VLSI topics. The main advantages of the VLSI is minimum size. Okay. So we can vary the width and the length of the transistor in the EDA tool. EDA tool is nothing but our company based tool like Cadence, Mentor Graphics, and then Tanner. This digital schematic is an open source tool. We cannot change the length and width of the transistor. Okay. So now, as for now, we have just placed the PMOS transistor and then NMOS transistor. And what are the things we have to do? Now we have to connect the PMOS and then NMOS. So for connecting the PMOS and then NMOS transistor, we can make use of the line. Okay. So the line, it will be available with this arrow mark. Okay. So when we move the cursor onto this icon, it will display add a line. Yes. The same with the clicking this, you can find the icon has been selected. So this yellow corner. Okay. So you have to make a connection between this yellow and then this. So the software will itself automatically make it as a straight line. So you not need to worry of drawing a line. Okay. So now we have connected the PMOS and then NMOS, and also we have to connect these two lines. Okay. So now we have just drag and drop the PMOS transistor and NMOS transistor, and we have connected both the transistor with the help of line. So as the third step, we have to provide an input to the CMOS inverter. So for providing an input, here we have an button which is called as an input. So where the first button, it will have a blue color here. Just drag and drop. It will display as IN1. So since it is an first input, it will display as a IN1. So again, we have to connect a input and then this connectivity. So just draw a line between IN1 and then this connection of CMOS inverter. So now I have provided an input and I have to check with an output. For an output, here this library will have in the second line, it will have on the light. So it just as a LED light. So again, you can drag and drop the LED lights. Okay. So again, we have to make a connection of this output and then CMOS inverter. Again, I am clicking in the line button and adding. So make the line of CMOS inverter and then output button. Okay. So as for now, again, I am repeating. I have opened the software page of dsch2. It is nothing but a digital schematic with the version of 2. So after opening the tool, here we will find a symbol of library functions. In this symbol library, you can find a PMOS, NMOS, NOR gate. Okay, with the several components it will have. So as for your first trial of experiments, now I have designed a basic of CMOS inverter. The basic of CMOS inverter will have both of PMOS transistor and then NMOS transistor. And then we have to make a connectivity for input and the resultant will connect it to the output. So for PMOS inverter, I am searching in the library. It will have in the bottom to the second line. Just I am drag and drop the component. Okay. So PMOS and then NMOS. So if suppose I have wrongly misplaced the components, how to remove it? How to remove a misplaced components or wrongly connected? So here you can find a gun icon. So when we have moved the mouse cursor to the icon, it will display as a cut. So after clicking the cut button and you can shoot it out. What are the things you have to remove from the layouts? Okay. So at once you have removed the icon, you should press the escape so that the gun icon will be released. Otherwise, wherever you're clicking, the components will be erased. Okay. So now we have made the connection of inputs and then outputs. Now what are the rest of the things is that we have to provide an input supply voltage. So for the VDD supply, in the same library functions at the top of the page, it will have a supply. Okay. So again, I am clicking on the supply and drag and drop the icon to the PMOS transistor. We are all well aware of the input supply. It should be provided only at the PMOS transistor. And the next, what are the things? We have to make a ground. So for the ground, it will be in an adjacent of the supply. So just click on the ground and drag and drop the ground. So as for now, we have make a connection of CMOS inverter. So this is the basic circuit of CMOS inverter. After drawing the circuit, you should save the circuits. For save the circuits, please follow the procedure. Click the file and you can find a save as. So select the save as. So for my convenience, let me save the file in a desktop and naming it as a inverter. So the save as type, it should be in a schematic. So the extension of the schematic is .sch. So let me save the schematic. And now I am running out of the simulation. So for running this circuit, you can find a run simulation button. Okay. So just click the run simulation button. You can find the connectivity. And also you can find the timing diagram. For the timing diagram, I have clicked the next icon of the run simulation button. So with this, we have draw a CMOS inverter with the current transition of 1 milliamps. So here I can expand the x-axis and then y-axis. So also I can increase the maximum voltage average power with the supply of the 1.2 voltage. So here comes, this is the basic circuit diagram of CMOS inverter and we are making the simulation. Okay. So as far the VLSI lab is considered, we have to draw the layout for the CMOS inverter. So here is the shortcut for making the layout of the CMOS inverter or differential amplifier or any flip-flop. So if you are well versed in the circuit diagram, you can convert the circuit diagram into the layout. So now we are entering into the second process, that is the designing of the layout from the circuit. So please note down the procedure. For converting the circuit into a layout, you have to go to the file icon, the same process of the save file icon. In this file icon, you can find a name called a make verilog file. You can find the make verilog file. Okay. So just click the make verilog file. You will show one code. You no need to create or rewrite the code. It will display the Verilog code for our CMOS inverter. Okay. So in this, you can find the bottom of the pop-up OK button. Just click the button of OK. Right. So as for now, again, I am repeating. Now I have opened the tool called as a digital schematic. In the digital schematic, I have drawn a circuit, right? After drag and drop the placing of the inverters of both PMOS and then EMOS, NMOS, I have connected with the inverter and then outputs. After connecting it to the inputs and then output, I have placed the VDD supply voltage and then ground. So after connectivity of all the circuits, I have saved my files. After saved my files, with the help of run simulation, I have verified the resultant. So now, as the second step, I have to convert this circuit into one layout, and the layout, it should be run with the simulation. So for designing and layout, I have converting. In the conversion process, the first step is the click. We should click the file icon. In this file icon, it should be a make verilog file, right? So just have this page, and now we have another tool which is called as a microwind. So this is a digital schematic where the next is a microwind. Again, this microwind also an open source tool. Just double click and open the. So here you can find the microwind with the image of an IC. Again, the version of microwind is an microwind 2. Just to open. So you can here you can find out the layout design page. It is almost similar to one digital schematic. Again, the gun icon for the delete some layouts here all. Okay. So here we can find some of the palettes, that is nothing but a library. So as we studied in a subject, it should have then N-well region, P-well region, and we have to make a silicon. After a deposit of the silicon, it will make us a SiO2 layer, and we should make a contact between the PMOS and then NMOS, or we should make a contact between source, gate, and then drain. So for the each and every process, that is, what are the things we are studying in a VLSA layout design rules, here we can frame it. Okay. So N diffusion layer, P plus diffusion layer, and making a contact between one layer to another layer. We will find a metal 1, metal 2, metal 3. So each and every layer, it will have an individual color. It is an unique. So say for example, if we are drawing an anvil, it will have like this green color display. If we are placing a metal one, the metal one will have an this blue color structure, where the metal two, it will have some more thicker than this metal one layer. So this the color variation itself, it indicates this is an anvil region. We no need to represent as a sketch. So what we say, while we have studied in the biology, after drawing the diagram, we will name the parts. Okay. So like this, like that biology subjects, here we no need to mention any parts of the diagram, because the color itself indicates what it represents. So say for the polysilicon, it will indicate as the red color region. Okay. So for the metal 4, we are connecting the fourth metal, means it will display in the green color with the lined of diagrams. Okay. So this is just if you are expertise in designing a layout as a straight, we can use with the help of the palette, we can draw the layout. So since we are in the starting stage, we are with the help of the circuit, we are converting. So let me back with the procedure. So make a file, new, no need to save this layout. So as for now, with the help of the digital schematic, we have created the Verilog code. Okay. So now what I'm doing is, I'm going to compile the Verilog code. Okay. So for that, after opening the microwind, just click on the compile. You can find a compile one line and then compile Verilog file. So in the digital schematic, we have created a Verilog file. Okay. So just click on the compile Verilog file. So for now, we have to open the Verilog documents. For opening the Verilog documents, just to go to the page or location where we have saved the Verilog file. So as for now, I have saved the Verilog file in the desktop. So I am clicking on the desktop. Here you can find with the name of inverter. Okay. So the inverter is nothing but the circuit which we have created in the digital schematic tool. So after creating the digital schematic tool, we have converted the circuit into a Verilog code file. Now, with the help of Verilog code file, I am drawing a layout. So just click the inverter and click the open. Okay. So again, it will display the Verilog code file. It's nothing. So in the bottom of this page, you will find a compile. I hope it's visible. It's now some more clarity. So you can find this compile, right? So just click on the compile. Okay. So after click on the compile, you can find the layout of inverter. Okay. The size of the inverter, it may varies from the basic design to the conversion process. The conversion process is what we have adapted the method of drawing a circuit and converting into the Verilog file. From the Verilog file, now we have created the layout. The layout will have the PMOS and then NMOS transistor with an input and then output version. Okay. So after the fetching of the layout, now we have to save this file. So again, click on the file, save the layout, or click on the save as. The save as, you can choose the name of inverter. So after saving the layout file. Now we should run this layout simulation. For running this layout simulation, again, click on this green icon. It will show the run simulation. So click the run simulation. You can find a waveform. Okay. So more than a waveform, you can find this right side parameter, the power of the inverter. The power of the inverter is 2.405 microwatts. Okay. So also here it will display the x-axis and then y-axis. And then as we have studied in the digital signal processing, this it will come under the FFT. FFT is what? Fast Fourier transformation. So the butterfly diagram of DFT and then DAT. Okay. And also, okay. So look. So here the power is the 2.40 microwatts. Okay. So if my consideration, the power of the inverter should be only the 2.4, even a second, third value after the decimal, it should not be. Means we have to again redraw the circuit and redraw the layouts. Okay. So after these changes, we should try what may the power level. Okay. So since it is an open source tool, as I said already, we cannot edit the size of the transistor. So, but after the EDA tool of the Cadence or Mentor Graphics, we can vary the length of the transistor and we can reduce the power consumption. So again, I'm saying the main advantage of the VLSI is the minimum power consumption with the minimum size. Okay, the minimum size, the minimum size of the products or minimum size of the processor, it starts from the minimum size of the transistor. Okay. So again, now I am going to recall what are the things now we have seen. So as for now, I have opened the digital schematic tool. So after opening the digital schematic tool, I'm closing all the tools what I have opened. Save the layout now. Okay. So in the after clicking on the digital schematic tool, let me finish it quickly. So just come down and you can find the digital schematic. Just to double click the software tool. In the right side, you can find the library function. As the initial, I have drawing the basic CMOS inverter. The basic CMOS inverter will contain the PMOS transistor and then NMOS transistor. So just click on the P channel MOS and just drag it and place it. Okay. So again, next NMOS transistor, right? And the power supply. The fourth is the ground. Now we have to connectivity the inputs and we have to place over the outputs also. For an output, I have placed over the LEDs and then for an inputs, I got placed over the buttons. So with the help of the line, I'm connecting with the inputs and then outputs. So now I have made a connectivity and now I need to save this file. So again, I'm typing save the files into the desktop. So with the name of the inverter example 2. So for my variations, I have named this file. So after this, I am clicking on the run simulation. So after the simulation results, I'm converting this circuit into a Verilog file. The purpose of converting this circuit into Verilog file is I need to draw and layout and I have to make a simulation. So for this purpose, again, I'm clicking on the file. At this file icon, I'm clicking on the make Verilog file. So with the help of the make Verilog file, I'm just clicking on the OK. So now we have finished with the first step, that is designing of a circuit. So after this, just leave the page of the digital schematic. Now open the folder with the name of the microwind. So in this microwind, you can find the tool name with the image of the IC microwind 2. So now here the microwind software tool has been opened. Here now click on the compile. In this compile, you can find the two. One is the compile one line and the compile Verilog file. We have created the Verilog file. So with the help of compile Verilog file, I am selecting the text file. The text file is nothing but the file which I have saved for the Verilog. Okay. So in the desktop, I have named it as an inverter example 2, right? So with the same name, you have to open the same file. You should be open inverter example 2. So after this, after clicking on the file, you can find this box with the name of Verilog file and the Verilog code. In this bottom, you can find the compile. On the left hand side of this, you can find the compile. So just click the compile, right, and close. You can find the layout of an inverter. You can find an layout of the inverter. So after finding, come up with this layout, just save the file as a save as example 2, save it. So after save this layout, just click the run simulation. Okay. So by clicking this run simulation, you can find a waveform with respect to an inputs. So here you can find, I think it's some more visible, I think. The green color, that is an input, where the green color is an input where we have drawn with the basic CMOS inverter. It's nothing but if the input is the 0, the PMOS will be the high. Where the input is the high, the PMOS output will be then low. Okay. So here you can find this again, the power value, right? I hope everyone now understood how to draw a circuit and how to convert the circuit into a Verilog file. And from that Verilog file, how we can convert the process into a layout. So from this layout, we have to make a simulation. So these procedures has been applicable for both our analog IC design laboratory and then VLSI design laboratory of the second cycle experiments. In the VLSI design laboratory, we can find flip-flops, CMOS inverter, CMOS layout, differential amplifier. For the 4 to 5 experiments, the same procedure and the same it will applicable for an analog IC experiments also, right? So with this, I am ending up my video. Thank you.